Okay, so let's suppose we have a function here, f of t, and a of x is equal to the integral from 0 to x of f of t dt. So this is the area collecting function, notice, starting at 0 and then going up to whatever x is. And so let's find the first part is find a of 3. And so this one's easy because all you have to do is plug in 3 into x. And so that means that we're looking for the integral from 0 to 3 of f of t dt. Okay, now this is equal to the area underneath f of t from 0 to 3. So if you go from here to here, 1, 2, 3, the height is 5. So this is just going to be 15 over 2. Base times height over 2. It's a triangle, right? Okay, now to find the derivative of that function at 3, we have to use the fundamental theorem of calculus, which basically says, okay, well, the derivative at 3 is equal to f of 3. So basically the value of this function evaluated at the x value. And so that one is even easier. That's just at 3, little f of t is equal to 5. Okay. And now what we want to do is try to figure out a way to graph x's. So I'm just going to draw a rough sketch over here. Now this is going to be a graph of a of x, the area collecting function. Now just think about this for a second. What is going to be the general shape of a of x? Well, notice that as you go from 0 along here, you're always going to be collecting area. And so this one is going to be always increasing, right? So that's just kind of a little note to self. Okay, so we know that at 3, the value is 15 halves. I'm going to just label this 15 halves. Okay, and then at x equals to 5, if I find the area from here to here, why don't I just kind of make that into those two little shapes. So this is going to be, this one has an area of 4, and this one has an area of 2 times 3, which is 6 over 2, so that's 3. So this area right here is 7. So that means that I'm going to go from here to here, from 3 to 5. So this is 3, it's 15 halves, or 7.5. I'm going to go another 7. So we'll call that 14.5. And so we go from here to here in this way, and then from here to here. Now it's hard to kind of tell because my axis is off, but you know, it's going from here to here. It goes in at a different rate than from here to here. Not a big difference, but a little bit. Okay, and then from 5 to 8, that's 1, 2, 3, so that's 6. So from 5, 6, 7, 8. You'd go up another 5, so that's going to be 19.5. And so, you know, roughly, that's kind of what it looks like, sort of course. And this might be a little curvy, but that's good enough. Just a rough sketch. Okay, so this is a pretty interesting problem. We have a function y equals to the integral from 0 to x of 1 over 1 plus t squared. And it's asking to find where is it concave up. Now that's just bananas. I mean, what does this have to do with the concavity stuff? But really, I mean, this is just like any other function, right? And so to find the where it's concave up, well, you just follow the normal rules you would otherwise. You would find your pips, and then you do your number line thing. Sorry. Okay. And etc., etc., etc. So you know what to do. So the first thing we do is we have to find the second derivative. So to find the second derivative, well, I have to find the first derivative. So the first derivative of this function, I just used the fundamental theorem of calculus part 2, which just says, so I'm going from a constant to x, just plug it in. So this is just 1 over 1 plus x squared. Okay, so then the second derivative is just the derivative of this one, which means I need to use the quotient rule. So, okay, well then I would have the derivative of the top, which is 0, times 1 plus x squared, minus 1 times the derivative of the bottom, which is 1 plus 2x, all over 1 plus x squared is equal to 0. Okay, and then I find my pips. Beep, beep. Okay, so this whole part right there is equal to 0. Let me do it with blue. And so then I have negative 1 plus, negative 1 minus 2x, right? And so that's going to be x is equal to negative 1/2. So that's what I get from this one for a pip. Now for the bottom, this one, there is no solution to this one. So I'm not going to worry about it. So this is my only pip. My one and only pip. Okay, so now got my number line, negative 1/2. And I'll test some points. How about negative 2 and 4? No, how about 0? It's much easier to do 0. Okay. Alright, so I'm going to plug it into the second derivative. Now, let me simplify this a little bit. So y double prime is equal to negative 1 minus 2x. Oh my goodness, I totally forgot the squared down here. Sorry. When I did the quotient rule. Terrible. But I caught my mistake, so that's okay. Alright. Over 1 plus x squared. Squared. Almost forgot it again. Okay. So then, y double prime at negative 2 is equal to negative 1 minus negative 2 minus 2 times negative 2 over the bottom. I don't even care what it is because I know it's going to be positive because it's squared. And so this is equal to negative 1 plus 4, which is positive. Which means it is concave up. Okay. And then I plug in 0 and I get negative over positive. And so, trying to get the right color here. Negative, which means it's concave down. And so then what I'm looking for, the interval, what the question is asking for is where is it concave up? So that would be right here. So it's concave up on the interval from negative infinity to negative 1/2. And that's it.